Okay, for the last 2 days we have spent our time learning how to find the derivative of an implicit equation. Okay, an implicit equation. And I want to, first thing I want to do here is draw your attention to something that you studied last year, something called conic sections.
Oh, yeah. Is that an eraser?
No, it's a piece of wood. So, conic sections, equations, these are the parabolas, the ellipses, hyperbolas, and so on. And they can all fall under this category of an equation that is ax squared plus by squared plus cx plus d, well that should be dy, plus exy is equal to f. So let me change that. And if you then modify these values, which I've got one of these, I got a slider on each one of these. Okay, based upon the values, whatever those are, they give you any one of the conic sections. Okay, so you can get a parabola, this, or an ellipse, or a hyperbola, and see what this one, add d and add f here. So you can even get a circle out of this based upon the values. So wanted to show you that, first of all, the derivative, first of all, the conic section can allow us to graph any one of these. So I'm going to just pause this thing and let's create something, and then we'll find the derivative of it to show you what we can do. So I don't know, we'll see what we get here. We got a 1 there. We got a 3 here. We got a 2 here. Maybe a 1 here. And let's do 3 here. Okay? So here is this ellipse. What we're going to do is we're going to find the derivative of this equation, okay, which would then be allowed to find the slope of the line tangent to that ellipse at any given moment. So we're going to write out that one and then go ahead and find the derivative. So what do we got here? So we're going to find dy dx. And we have 1x squared plus 3y squared plus 2x plus 1y. I don't have e. Where's my e? E. Oh, I can't use e. It was using 2.71. E can't be used as a slider because e is a number. It's like using pi. E if g. So we'll add a slider of g. And g is at 1. Well, now it's this parabola, this ellipse right there. What does that value do? It does this. So we'll put it, let's stick it at 3. So this is plus 3xy is equal to f. Anybody remember what f was? 3. Okay. So this should be a piece of cake based upon what we've been studying for the last 2 days. So we are finding the derivative of this ellipse, which happens to be this equation, and we're going to find the derivative of it. So let's go do that. So from the beginning, we just go from left to right. We're finding the derivative of every single term. Derivative of x squared is 2x plus the derivative of 3y squared, 6y times dy dx. And if you read in the book on implicit differentiation, you'll see that they use y prime. Okay, they say multiplied by y prime. I have chosen not to use y prime because it looks too much like a y to the first. Okay, so I'll always write it as dy dx. Okay, plus derivative of 2x is 2, plus the derivative of y dy dx, plus the derivative of 3xy, product rule. So, and for the sake of it, I'm going to put the xy in parentheses, and the derivative of a constant times the product of two functions is the constant multiplied by the derivative of the product, which we're going to use a product rule. Okay, we're going to use a product rule on x times y. So 1, that's the derivative of the x, times y, bless you, plus the x times the derivative of the y. That's your product rule. First, so we did the derivative of the first times the second plus the second times the derivative of the first. And then this whole thing is equal to the derivative of 3, which is 0. So that's the calculus step. Now we're just going to do a little algebra. So we're going to solve for dy dx. So I'm going to just rewrite this term and distribute the 3. So 2x plus 6y dy dx plus 2 plus dy dx plus 3y plus 3x dy dx is equal to 0. All I did was distribute the 3. Now we're going to leave all of the terms that contain a dy dx. We're going to leave them on this side. And we're going to put all the terms that do not contain a dy dx on the other side. So this gives us 6y dy dx. I'll check mark these here. Plus a dy dx. It's that one. Plus 3x dy dx. It's that one. Equals. Then we'll put the other two terms on the other side. So that's going to give me a minus 2x, minus 2, minus 3y. Then, since these all contain a dy dx, we're going to simply factor out the dy dx and then divide. So 6y plus 1 plus 3x times dy dx is equal to negative 2x minus 2 minus 3y. All I did was factor. Don't forget that 1. And then, therefore, dy dx is equal to negative 2x minus 2 minus 3y over 6y plus 1 plus 3x. This expression tells you the slope of the line tangent to that curve at any given values. Okay? Now, I'm going to just show you a little algebra thing here. If you happen to put all your dy dx's on the right side, you know what I mean? And left all of the terms that did not have the dy dx's on the left side, you would have ended up with this. See what the difference is? It's exactly the same thing. Okay? It's just that every single term has changed from a positive to a negative or a negative to a positive. Its sign was changed. It's the same as me as multiplying the top and the bottom by -1, which doesn't change the equation at all, or the expression. Okay? So, I'm telling you this because on the AP exam you might do an implicit, this would be a classic problem you'd see on the AP exam, multiple choice. You get this for an answer, but you don't see anything like that there, you see this one. Okay? But so if you switch every single term to its opposite, this one is also okay. It's just you put your dy dx on the other side than the person that solved it. Okay, now I don't know if there's a point that we can test at this, so I'm going to see if I can get one here. This one almost seems, oh, look at that, -3, 0. Okay, so let's write the equation of the line tangent to this curve at -3, 0. We're writing the equation of the line that's tangent to that curve at -3, 0. So the line should look something like this when we're all done. So, in order to write the equation of the line, what do we need? A point and a slope. Okay? So, let's do the slope first. So the point is at -3, 0. So I'm going to take this derivative and I'm going to plug in -3 and 0. So you check my work here. -2 times -3 minus 2 minus 3 times 0 all over 6 times 0 plus 1 plus 3 times -3. 6 minus 2 is 4. So I got 6, I got 4 here. 4 over -8. I got -1/2. Okay, so the slope is a -1/2. The negative seems good. So let's write the equation of the line. This is going to be y minus 0 is equal to -1/2 times x plus 3, which is y is equal to -1/2 times, well, I'll write it like that, -1/2 x minus -3/2. So if I graph this, it should be close to that green line. So y equals -0.5 minus 1.5. And you got to put x in there. How close did we come? Not bad. Okay? So, what you just saw here was a big picture deal of, you can take any conic section, you can find the derivative of it, which then allows you to find the slope of the line tangent. Notice that you use both the x and the y, because there's also another place right here that has an x value of -3. So you have to use both the x and the y coordinate to find the slope. That's a critical thing, because these things fail the vertical line test. They're not functions. So you have to use both x and y to find the slope. And then find the equation of the line, boom, 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 and you're done. Okay? All right. So this was a kind of a quick recap of what we've done over the last 2 days, being able to find the derivative implicitly. Today we're going to finish off with the last part, which is how to find the second derivative of any given equation. So let's do that right now. I'm giving you an example. Find the second derivative of x squared plus y squared equals 16. We good? Okay. Debating?
Yeah.
Oh, I know. It's always that tough thing. This one deserves its own page. We'll make it easy. Okay, so step one. So step one, what do you think step one is? Yeah, find the first derivative. So, you guys can do this. You do it and I'll do it. We'll see if we get the same answer. Okay, you get negative x over y as the derivative of the circle. Okay, so step two. What do you think step two is? Find the derivative of the derivative. Okay. So find the derivative of the first derivative. And so if I start off with dy dx equals negative x over y, and I got to find the derivative of it, we're going to take the derivative of both sides. So this is where that notation comes in. D dx of this equals d dx of this. And so we have... Okay. So I'm finding the derivative of both sides, so I'm showing you the notation here. And this is where, when you take the derivative of dy dx with respect to x, this is where it becomes d squared y over dx squared. If you want to, you can just think, well, there's two d's on the top, that's why it's d squared. Technically not, but it's like a good mnemonic. And then dx times dx is dx squared, and the d and the x are glued together. They make one term. Okay, right side, how do we find the derivative of negative x over y? Quotient rule. So here we go. Bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Got to have that quotient rule down. Make a song. Okay, I'm just going to clean this up. So negative y plus x dy dx over y squared. So that's just that one cleaned up. Now, what you should observe is that the second derivative, we'll go back here. The first derivative contained both x's and y's. The second derivative contains x's, y's, and first derivatives. See that?
Could you like plug in?
Step 3.
Hey.
And step 3 is to replace dy dx. Okay? Plug it in by substituting what it's equal to. So your final answer is only going to contain x's and y's. So what was this originally? This is... So I took the dy dx, which was right here, and replaced it with what it was equal to. Okay. Now the second derivative only contains x's and y's, and we should probably clean this up. Okay. What should we do to clean it up? Any suggestions? Multiply by... I'd multiply by y, because that's the one that's on the fraction here. So multiply the numerator and denominator by y. It doesn't change the expression at all. It writes an equivalent one. So now I got to distribute that. So this is going to be negative y squared. The y here cancels with the y here. So it's going to be minus x squared over y cubed. Notice what happened here. Y times negative y squared. Y times negative x over y, y's cancel. So it's just left with negative x times x, negative x squared. Which can be rewritten, therefore, d squared y over dx squared is equal to negative 16 over y cubed. Where did that negative 16 come from? Go back to the original equation. Equations were born to be manipulated. So if this is equal to this, then negative 16 is equal to negative x squared minus y squared. Which we could replace that. Make sense? So that's weird. The second derivative only contains y. It's only dependent on y. That's interesting. I wonder why that is.
Did you ever figure out the infinity?
No, but I did it. We picked a different problem in the next class, and we had the same problem. So that's something that's got to be thought about.
Should we find the third derivative?
No.
Yeah.
No, I don't have room.
Okay.
I'm not writing this down. Formal protest.
Oh, well. Yeah. Well, what if you can do third derivatives or fourth derivatives, then you can do second derivatives, piece of cake. All right, here we go. Now. Yeah. So I'm going to rewrite this. We could use quotient rule, right?
Yeah, let's not say it.
But we could actually rewrite this. Right?
Do you have to use the quotient rule if you do that and then do the product rule?
Well, this we're going to end up using just the standard power rule. If something, normally when you see something like this, like over this, then you're going to attack it with a quotient rule. But bypassing the product rule, I can go right to the power rule with this. So this means that d cubed y over dx cubed is equal to the derivative of that, negative 16y to the negative 3. Which is equal to, what do I got? 48y to the negative 4 multiplied by the derivative of y, which is dy dx. So it's 48 dy dx over y to the 4th. And it's standard practice not to leave any derivatives in a derivative answer. So we have to replace the dy dx with what it is equal to. So this is equal to 48 times, what do we got for our first derivative? Negative x over y to the 4th. And then multiply by what? I'd multiply by y as well. So top and bottom by y. And final retail answer is negative 48x over y to the 5th. This is third derivative. And we keep kind of going and going and going if we wanted to. Let's see. If we consider it as motion, the function itself is position. The first derivative is velocity. Second derivative is acceleration. Third derivative is jerk. And then fourth derivative, I can't think of what it would be. Change of jerk. Jerk is what happens when your coffee spills when you're driving your car. So if you got your coffee and you're on cruise control, coffee's not going to spill. If you are, and that means that we just have a constant velocity. Okay. If you're accelerating, you're going onto the ramp or on the on-ramp to the interstate. Does your coffee spill there? No. It may hover a little bit, Okay? Because there we now we have an existence of acceleration. Okay, we have acceleration that is existing. But the only time you really spill your coffee is if you either slam on the brakes or you hit something and you have a sudden change in acceleration. Then you have a jerk. You hit it like the jerk that cuts you off. Yeah. Okay, Christina? I didn't randomly pick on her. She had raised her hand. Yeah? This one? Yeah. It's the power rule and then the chain rule as being where y is a function of the x. So yes, we're applying the chain rule and power rule on the y. Because it's negative 16 times something to the negative 3. So the derivative is the negative 16 times the negative 3 times something to the negative 4th times the derivative of the something. Two times dy dx. What is it?
They call it snap, crackle, and pop.
Oh, really? The derivatives after jerk are snap, crackle, and pop.
Someone who's either really hungry or eating one is jerk.
The fourth one is snap. So the fifth is crackle and the sixth is pop.
Oh, okay. Is it still after jerk? Or is snap jerk?
Snap is jerk.
Snap is jerk. Okay. Okay, let's do it again.
Lock and drop are the... They look like actual names.
That's crazy. Okay, new one, find second derivative. We're just going to do this again. So find the second derivative of this. And should we do this one together? If you want to do it on your own, do it on your own. I'm going to do the first, I'll do the first derivative here. All right, you guys get a head start on that. See if you can find that correctly, and then we'll then I'll start at it. Now this is where the algebra can get a little funky. This is what this thing looks like, by the way. Wasn't that funny?
It's kind of funny.
Anybody get that? First line is the most important. Got to do product rule on this guy right here. Now, just so you see the step here, I use the power of factoring to extract the 2 so we could cancel the 2's. Okay, this one could be good. Piece of cake. Let's see, I gotta double check my. Yes, we're doing the product rule inside of the quotient rule, while we're doing implicit differentiation, which uses the chain rule. This will be problem number 1. Then it gets hard. All right, I think I got it. Okay, should we walk through it? Okay. We're finding the derivative of this, so we have to use the quotient rule. So we recognize that we have a top function and a bottom function. So when I talk about top and bottom, that's what I'm talking about. This guy and this guy. So quotient rule says this. It's the bottom times the derivative of the top. This is the derivative of the top function. The derivative of the 1 is 0. Minus, now we have to do the product rule on x times y squared. So, derivative of x is 1 times y squared plus x times the derivative of y squared. So this is the product rule on xy squared. Okay, that's just the first part. So it's bottom times the derivative of the top minus the top times the derivative of the bottom. So this is the derivative of the bottom. It's the derivative of x squared y. So it's going to be 2x times y plus x squared times dy dx. And it's all over the bottom squared. Piece of cake.
That would not be your final answer, would it?
No. So now we're going to just clean it up once, and then we're going to replace our dy dx with what it belongs with. So this is x squared y times y squared plus 2xy dy dx minus 1 minus xy squared. What? Negative. Distributing the negative there, thank you. 2xy plus x squared times dy dx. And don't forget your bottom. X to the fourth over y to the fourth, or y squared. That's not so bad. And then now, everywhere you see a dy dx, you're going to replace it with this. Question?
Where did the minus sign after the negative y squared come?
Minus sign after the y squared. This one? Distribute here, here. That's distributing the minus. Okay, here we go. Real quick. X squared y times negative y squared minus 2xy times 1 minus xy squared over x squared y, parentheses, minus 1 minus xy squared times 2xy plus x squared times, parentheses, 1 minus xy squared over x squared y, parentheses, all over x to the fourth y squared. Now find the third derivative. All right, all your homework's got to be done by tomorrow for implicit differentiation. And the videos will be online.